All right, good afternoon. I did forget the iClicker question, but I was able to sprint back to my office and get it for us. Thank goodness, I know. That would be such a letdown. All right. All right, SI session tonight. Be there or be square. Quiz 5 will start. Okay, let's quiet down. Quiz 5 will start this week. It's not up yet, but I'll try to get it up right after class. And we are in the midst of talking about various additional equilibria. Right? So we've gone from just acid-base equilibria to now what happens if we add a common ion. So usually, or oftentimes, that means adding extra conjugate base to the equilibrium, right? And we've seen how we can calculate the pH that would be generated when we do that. So it's essentially a quantitative approach to Le Chatelier's principle, right? We did it qualitatively before, and now, at least in acid-base reactions, we know how to do it quantitatively. We went in and talked about neutralization reactions, because those are important when we get to this next step, which are the titrations, right? Because when we do titrations, what we're always doing is taking either a strong acid or a strong base and adding the opposite to it, right? Or a weak acid or weak base and adding a strong acid or a strong base. So we're always we have I showed you the picture, I don't have it up here now. We have the burette, right? And that's how we add the second component to the titration. The one that's in the burette is always either a strong acid or strong base. Okay? Because what we need to do, why would it have to be that way? Why would we want that one to be a strong acid or strong base? Because when we add that, if we're going to go based upon the volume we add, we want to know exactly how many moles that is. And we want to make sure that all of that we add reacts completely. So, for example, the base that we drip in, if we use sodium hydroxide, because that initial reaction is a neutralization reaction, we know that neutralization reactions always go to completion. Okay, so every mole of sodium hydroxide we drip into the flask is going to react. Okay, so we know that's going to be quantitative, right? If we were adding a weak base in there, we couldn't say that, right? It'd be very complicated then to use our Kas or Kbs for every drop we add to calculate some new equilibrium. All right? So, we know that, a very important thing about these neutralizations is they always go to completion. So we're using that then to do these titrations. And we already did several calculations where we did this titration of a strong acid with a strong base. Right? And when we did that, we got a titration curve that looked something like this. So this is the volume of NaOH added, and this is the pH over here, right? And so let's say that the pH in the middle is pH 7, right? So if we're starting with a strong acid and we're adding in a strong base, where would the pH start? Would it be a low pH or a high pH? Low, right? Because we're starting with an acid and we're adding base to it. So it's going to start at some low pH here. As we gradually add more sodium hydroxide, the pH is going to go up gradually until the amount of hydroxide that we added becomes very close to the amount of acid that we had present. And in that point, the relative change in the hydrogen ion concentration changes very rapidly. And so we get a very sharp curve that goes up like this, and then it levels off once we now have an excess of base. Right? There was a point in the middle, I guess somewhere here in the middle, which should correspond to this. And what was this called? the equivalence point. This is where the number of moles of base added equals the number of moles of acid. Okay, so this is the equivalence point. Okay, and it's the amount of base equals the amount of acid. Okay, and when we do the titration of a strong acid with a strong base, what's going to be the pH of the equivalence point? It's going to be at 7. Okay? All right, so we'll find that this changes a little bit when we do the titrations of weak acids with strong bases. Okay, so there's going to be some changes now. And we started into some of those. I think we started into our first calculation. And we'll finish that and do another one. And then we're going to apply this to a system which we call buffers. And remember I mentioned the other day that buffers are systems that resist changes in pH upon addition of acids or bases. Okay? So, any questions on this up to now? Nope. Okay, so let's do that iClicker that I sprinted up to my office for. So there it is right there. Okay, so this is the stepwise thing that we were doing for this weak acid strong base titration. I don't think we did it exactly this way. First thing we had to do is convert the volumes of acid and base, the volumes and the concentrations to moles, right? We calculate molar quantities of the acid and the base that was added. We then identify the limiting reactant, and we determine what acid or base is left over, is in excess. Okay? So we determine the number of moles that remain after the neutralization reaction. We know that neutralization reaction goes to completion. Then we convert those moles into to molarity, to concentration. Okay? And so then those are our equilibrium concentrations, and then we just plug those into our equilibrium calculations like we've done before. Okay? So it's only really this first part involving the neutralization reaction. It is something new that we haven't already done. Okay, we have these three scenarios. We have where OH, the strong base, is limiting, means we have excess weak acid. And in that case, we started one of these, we do a common ion calculation because we have both acid and conjugate base in solution at the same time. We'll do another calculation after that where the hydroxide equals the amount of acid. So this is at the equilibrium point. And so the only species that we have in solution that impacts pH is just that of the conjugate base. And so because the conjugate base of a weak acid is also a weak base, we have to consider how that weak base can influence the pH. So we do that together with knowing the Kb for that base. And we'll do an example of this. And then when the acid is limiting, it means we have excess, say, hydroxide, then all we have to do is calculate the pH based upon the excess hydroxide in solution. Okay? And this is essentially the same as for the one where we use a strong acid and a strong base. After the equivalence point, it's the same in both cases. For strong acid, strong base. Okay? So I thought, we'll redo this. Okay, so the first one that we were doing said, what is the pH, okay, when after 50 milliliters of 0.1 molar acetic acid are titrated with 40 milliliters 0.1 molar sodium hydroxide. Okay? Okay, so the first thing that we did was just to write out the neutralization reaction. Okay, so we have to figure out what takes place with the neutralization reaction first. Okay, so what we're doing is that we have acetic acid, right? So acetic acid, and we are titrating that with hydroxide, with sodium hydroxide. So do we have to put the sodium in when we do this neutralization reaction? No, the sodium cation is not going to impact anything. So we can just consider the hydroxide. Okay? And should we have an equilibrium arrows here or a one-sided arrow? One-sided, right? Because we know the neutralization reaction goes to completion. It's only one direction. Okay, so if we do this, we get acetate, which is the conjugate base, plus water. Okay? So now we have to plug in how much we start with, right? And we have to do this in moles. So we have to convert the volumes, so 50 milliliters of 0.1 molar acetic acid, into the number of moles, right? So I'm not going to write out again. So 50 milliliters, how many liters is that? 0.05, right? So 0.05 times 0.1 molar is we have 0.005 moles. Okay? For the sodium hydroxide, we have 40 milliliters of 0.1 molar. So that's going to be 0.004 moles. Right? So now what we have to do is compare the two and determine which of these two are the limiting reagent, the limiting reactant. So the one that there's less of available. So which one is there less of? The hydroxide, right? 0.004 less than 0.005. So how much change is going to take place here then? Minus 0.004, because we know the neutralization reaction goes to completion. Minus 0.004. For every mole of hydroxide, it reacts with a mole of acetic acid. So this is minus 0.004. And for every mole of acetic acid that reacts, we're going to get the same amount of its conjugate base. Okay? And we don't care about water, right? So now we can add these or add them together. We get 0.001 of acetic acid. We have 0 left of hydroxide, and we have 0.004 moles. These are still in moles of sodium acetate. All right, so what's the next step that we have to do?
Convert back to molarity.
Right, we have to convert it back to molarity, considering the new volume, because we've added two solutions together. So the total volume is going to be 0.05 liters for the acetic acid plus 0.04 liters for the sodium hydroxide. So we get 0.09 liters, right? And so we're going to calculate that from this mole. So we go 0.001 moles divided by 0.09 liters, right? And so this equals 0.011 molar, okay, is the concentration remaining of acetic acid. Okay, so of acetate, we have 0.004 divided by, that's moles, divided by 0.09 liters, and this equals right here 0.044 molar. Okay? So essentially all we've done now is determine what species are available at equilibrium. Okay? So now we have to plug these concentrations into our equilibrium reaction. Okay? So our actual equilibrium reaction now is just the dissociation of acetic acid. Right? And in fact, we could do this as the acetic acid dissociating, or we could do it as the conjugate base reacting with water. We could do it either way. Okay, so let's do it. CH3CO2H is going to now be in equilibrium with its conjugate base plus a proton. Okay, so we put in the initial concentrations. That's what we calculated out here. And so we have 0.011. Yeah, I guess these are the initial, not the equilibrium yet. 0.011. Conjugate base, we have 0.044. These are molar. And what's the concentration of protons at this point? We just say it's 0 right now, right? That's what we're going to figure out. So essentially, what kind of a reaction are we, calculation are we doing now? Well, we got the acid dissociation. It is equilibrium, but we have the acid and we have its conjugate base. So what do we call this? This is the common ion calculation. Okay? This is what we're going to do down here. Common ion. All right. So, change. What's going to be the change in acetic acid? Minus X, right? It has to go towards the side where there's a 0. And so we're going to get plus X on this side over here. We're going to get plus X over here. Right? Final, we add these together. 0.011 minus X. 0.044 plus X and X. Okay? Now what do we do with these? Right, we have to use the Ka, which I'll give you now, which you would get if you were doing this problem. So the Ka equals 1.8 times 10 to the minus 5th. Okay, so the Ka equals concentration of product over reactants. Right, so we have 0.044. I'm just going to write in the numbers. Oops. I want to have. Let's see here. 0.044 plus X times X over 0.011 minus X, right? And this Ka equals 1.8 times 10 to the minus 5th. Okay, so what's going to be our approach to solving this? Shortcut, right? So what's the shortcut? Right, we can ignore the X's that are either added to or subtracted from some set value. Okay, so like this one right here. Okay, and the reason is, remember that when we do this equilibrium right here, oh, look at that. I got a finger on there now instead of the arrow. Giving you guys a finger. Remember that because this equilibrium constant is so small, it means that the dissociation has only taken place to a very small extent. So X, which is over here, or minus X here, these X's are very small. So when we add it or subtract it from some number, then we're subtracting or adding a very small value to or from it. And so it's going to be so small that we can just discount that. Okay, we'll cross this out, we'll cross this out. So, we get 1.8 times 10 to the minus fifth equals 0.0, I put too many zeros in there, didn't I? 0.44, that's too many. X divided by 0.011. Okay, we solve for x. We get x equals 4.5 times 10 to the minus sixth. Okay, so what does x equal here? What is it? The proton-ion concentration, right? Because it's right here. This is the one that we're interested in because we're calculating pH. So this equals the proton-ion concentration, so we can calculate the pH from that minus the log of 4.5 times 10 to the minus sixth equals 5.35. That's kind of small here. 5.35. Okay? Does that make sense? What do we have? So we're adding a base to this acid. We still have some acid left. So do we expect the pH to be above or below 7? Below 7, right? Because we have excess acid left over. And our pH ends up being 5.35, so it's below 7, so that's consistent with a qualitative analysis of the problem. Okay? Okay, right there. 8.72. So we were right up here. It's greater than 7. Okay? So with a weak acid, at the equivalence point, the pH will be above 7 because we have the presence of this weak base in solution, and it's going to make the solution more basic. All right? So we can relate this back to what we learned when we added salts to solutions. When we added the anion of a weak acid, we had a weak base, and that caused it to get basic. Okay, so here's another one. Okay, so this one says, okay, I'm going to go over here. What will be the pH at the equivalence point for the neutralization of acetic acid with sodium hydroxide? Let's say that it's so what's going to be the pH at the neutralization point? It's Kw, right, times 10 to the minus 14th divided by the pOH, which is 5.3 times 10 to the minus 6th. 7. This equals, I don't know if I did it this way here. 7. 1.89. Above 7? 0.89 times 3 choices, 10 right? To the minus 9th. Okay, well let's think about this then. Okay, so we got to do the same thing as we did last time. And we take minus the log of that, right, to get the pH. So, what do you think here? Is the pH look at the neutralization above 7 or below 7? So here's acetic acid. Let's look at that concentration of hydroxide. We know it's one direction, right? Goes to completion. We get CH3, CO2 minus. Plus right, the hydrogen ion concentration. Okay. So let's assume 1.89 times that the amount of acetic acid is the same as what we started. So that's less than 1 times 10 to the minus 7. Both concentrations are the same. The hydroxide concentration is bigger, so the pH should be greater than 7. So we had, and what we get here is milliliters, 8.7 of 0.1 molar acetic acid. Okay. And so now we're going to have, likewise, 50 milliliters of 0.1 molar sodium hydroxide. Okay, so we're at the equivalence point. We got equal amounts. All right, so should give us, if we do the same calculations before, 0.005 moles of acetic acid. Right? How much hydroxide? Okay, this time we got 50 mils of both of those, right? So now we have 0.005 moles of hydroxide. Okay? So what's going to be the concentration of hydroxide after this neutralization reaction? 0, right? So we know that that entire amount is going to react. It has to react over here, right? And we get the same amount over here, right? So we add these up, 0, 0, 0.005. All right? So what do we do next? The concentration, right? We got to go, this is in moles. Okay, we have to get the concentration, 0.005 moles divided by how many liters? 0.1 liters, right? Because we had 100 milliliters. So this gives us 0.05 molar solution of acetate, of the conjugate base. Okay? So now, because we only have the conjugate base present, it's probably best to just do the base reaction of the conjugate base. So we can say that the conjugate base, what's it going to react with? Water. In equilibrium to give us back our acetic acid plus hydroxide. Okay? Now, what all do we know? All we really know is the concentration of the acetate, right? 0.05 molar, right? 0 and 0. Right? So, this is initial change. What's the change? Minus x plus x plus x, total 0.05 minus x, x, and x. Right? Put it into our equilibrium expression. This time it's going to be the Ka that we use. The Kb is going to equal, okay, the concentration of acetate times the concentration of hydroxide over the concentration of acetic acid. Oh, it is. Thank you. I got those backwards. Okay. Let's see. Eraser. Maybe I can do it like that. Like that. So this is acetic acid here and acetate over here. Yep, products over reactants. So when we do this, we have x times x over 0.05 minus x. Okay, so what do we need to know in order to decide whether we can use the shortcut or not? We need to know the Kb. And if we use the same Ka we used before, 1.8 times 10 to the minus fifth. How do we get the Kb from that? Right, we divide the Kw by the Ka. right? So this equals Kw divided by the Ka. This equals 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. Okay, and so that should give us a Kb that equals, I have it here, 5.6 times 10 to the minus, I can't fit it, 10 to the minus 10th. Dang it. That is 10 to the minus 10th. Okay, so I'll write it in here. Equals 5.6 times 10 to the minus 10th. Okay, so can we use our shortcut? Absolutely, right? 10 to the minus 10th is very small. So which of these x's can we discount? Just the one in the bottom. Okay, so this one right here. Okay, so we get rid of that. Convert this over to x squared equals 5.6 times 10 to the minus 10th times 0.05, right? We multiply both sides by 0.05, and x equals wrong order. Okay, so here is kind of the titration curve of this weak acid, strong base scenario. All right, so notice, if you can see this, when we start the titration, we have a solution of weak acid. It is acidic, right? The pH is below 7, but it's not as low as it was when we were starting out with a strong acid in solution. All right? Otherwise, it looks at least qualitatively the same, right? So we have this area in here where we have excess. Well, let's not even say it that way. Where we have essentially our common ion situation in here. All right. When we get to the equivalence point, we have to calculate the pH we have from the conjugate base, from the equilibrium that is present with the conjugate base. And then, like we said up here, we calculate the pH from the excess hydroxide. All right? The one thing to note, if you can, when you look at this later, is that the pH, right, for a weak acid titrated with a strong base, the pH at the equivalence point is greater than 7. Okay? So these are the three scenarios. We've done this one, and now we just did this one, pH greater than 7. All right? This top one is just like we did for the strong acid, strong base. Okay? All right, so what would it look like if we reverse the titration? What if we started with a base and we titrate it with acid? Right? It would essentially just be the reverse of the titration curve. So here we're titrating a weak base with a strong acid. We are starting up here at a pH, right, that's basic, right? Because our starting point is with base. We add acid down this way. We would again have the common ion in here. Our equivalence point, notice now, if we started with a weak base, our equivalence point is less than 7. Okay, because we would have a solution of the conjugate acid. Right? And then down here, this would just be from the excess strong acid. All right? So they're also talking about in here, they've got this orange color, and this comes from what we call an indicator. All right? And an indicator is usually an organic molecule that has some acid-base properties. And what happens is when we protonate it or deprotonate it, we change its ionization state. It changes color. Okay? And so this can change color at some given pH. All right? And we have different indicators which can change at different pHs, change colors at different pHs. And so usually you select a indicator that has a color change near the equivalence point that you are, for the reaction that you're using. Okay? All right. Another type of acid is a polyprotic acid. Okay? So we looked at some of these oxyacids in the last chapter. So for example, this is an example with phosphoric acid. And notice that if this acid, so this is H3PO4. So it actually has 3 protons that it can donate. And so it will donate them sequentially. And usually the first proton that it donates is the most acidic. Second one is the next most acidic. And then the third one is the hardest to lose, okay? Just because we're building up a lot of negative charge on the conjugate base. All right, so we could look at this and decide, and we could write out 3 different acid-base equilibria, right? So phosphoric acid could give off 1 proton to give H2PO4 minus plus H plus, okay? That conjugate base can lose another proton to give HPO4 2 minus plus a proton. And there's even still another proton that can be given off. So then we can have a third equilibrium HPO4 2 minus dissociates to give us phosphate ion 3 minus plus another proton. Okay, so we should see an equivalence point for each of these acid-base reactions. Okay, so when we're in the middle here, so remember these flat zones are where we have the common ions, right? So in this section, we should have H3PO4 plus H2PO4 minus. Right? When we reach the first equivalence point, remember we have only the conjugate base of the acid. So here it says here at this equivalence point down here, we should just have H2PO3 minus. All right? Then as we add more sodium hydroxide, we go through another common ion situation. Now we have H2PO4 minus plus HPO4 2 minus. And at the next equivalence point, we have the conjugate base of this acid. So we have just H3PO, oh, those should all be O3s, I guess. Sorry about that. I guess I should go back and